Alright, in this video we're going to be talking about machines. Simple machines are everywhere around us. Let's dive in and start with levers. We're talking about pliers, nutcrackers, scissors. First thing I want you to write underneath your heading for levers, 1, 2, 3, F-R-E. And what that means is what is in the middle. You will always remember if it's a first, second, or third class lever based on what is in the middle. Okay, let's start drawing out these pictures and doing these examples with me. Pause the video at any time if I start talking too fast. First class lever has a mechanical advantage greater than or less than 0 depending on where the fulcrum is placed. A seesaw is a great example. 1, 2, 3, F-R-E. 1, first class lever. 1, 2, 3, F. F stands for fulcrum. The fulcrum is in the middle. First class lever, fulcrum is in the middle. Second class lever, it can't help but have a mechanical advantage greater than 1. Wheelbarrow, great example. I'm lifting on the left-hand side, my load of bricks or my load of whatever is in the middle, and my fulcrum is at the end. 1, 2, 3, F-R-E. Resistance, or my load, is in the middle. 1, 2, 3, F-R-E. Third class lever. Third class lever has to have a mechanical advantage less than 1. It can't help it. 1, 2, 3, F-R-E. My third class lever, my effort is in the middle. Great example, raking leaves. Let's pretend we're raking leaves with our right hand. My left hand is going to be the pivot. My right hand is where I'm putting in effort, and down at the end is where the resistance is. Okay, let's talk mechanical advantage. Mechanical advantage, commonly abbreviated MA. And we're also going to talk about ideal mechanical advantage, abbreviated IMA. Ideal, perfect. We're not considering friction when we're talking about ideal mechanical advantage. The equation for IMA is din over doubt. The D stands for distance in this case. Din means distance in, doubt means distance out. The distances are very important. So my din, 5.25 on this pair of pliers. The distance in, always, regardless of the type of lever, is from the effort, I'm talking din now, from the effort to the fulcrum. Effort to the fulcrum. My doubt is always from the fulcrum to my load, 1.75. 5.25 divided by 1.75, mechanical advantage of 3. The inches cancel, mechanical advantage is unitless. Now, little bit different. Let's talk about this example. Let's look at our measurements really closely, din and doubt. My din is always from the effort to the fulcrum. My doubt, I said, was from the fulcrum to the load. Now, in this example, look at my mouse. We did not have a load here, so we just went all the way out to the end. Sometimes you will see it as drawn or written as this. Sometimes, however, you may see it. You may see the doubt go to the center of the load. That's really common to see. So 5 divided by 2.8 gives me a mechanical advantage of 1.79. Another example. What kind of lever is this? 1, 2, 3, F-R-E, third class lever. The distances are the same, meaning we still measure from the effort to the fulcrum, just like we did on this one, from the effort to the fulcrum. And from the fulcrum to the center of our load. Same with this one, from the fulcrum to the center of our load. Those distances, at least the way that we measure, that does not change. 3.1 divided by 6.2 gives me 0.5. Remember, a third class lever has a mechanical advantage less than 1. Okay, let's switch gears. Actual mechanical advantage, reality, this time We're taking friction into account. AMA, actual mechanical advantage, equals Fout over Fin. The F stands for force. Force out, force in. Maybe I have a first class lever with a 12.3 Newton box, and maybe I'm pushing down with 5 newtons. You guys will measure this in class with a digital force meter. AMA, Fout over Fin, newtons cancel. Mechanical advantage is always unitless. Actual mechanical advantage of 2.46. Now, let's talk about a situation where you might have to find din or doubt, and you're only given mechanical advantage. This is where sometimes I say the lines between actual mechanical advantage and ideal mechanical advantage may be skewed a little. Maybe I have actual mechanical advantage in this lever system of 2.34. And the question says solve for din. Well, what I do is I take my actual mechanical advantage equation, I plug in the only mechanical advantage that I'm given, in this case it was AMA, and I use my ideal mechanical advantage equation. I'm solving for din, and it told me the doubt was 3.4. We cross multiply, that's how we get din of 7.96. So sometimes AMA and IMA can be skewed a little, especially if they're asking for din, but they only give you one type of mechanical advantage, like AMA, for example. Efficiency. Efficiency is AMA over IMA times 100. I used my previous example. 2.34 divided by 2.57 equals 91%. 91% is less than 100%. We're usually going to have efficiencies less than 100%. Okay, let's talk about wheel and axle. They are found everywhere. Bikes, go-karts, cars, skateboards. Notice we have the same equation. The equation did not change. But what's really important with wheel axle is to realize where the din and the doubt is. So distance in, maybe we're talking about this axle. Maybe this is I know it looks like a bike wheel, but let's pretend it's something that's powered, a go-kart wheel, okay? Distance in, so the input, whatever's driving the wheel, divided by doubt, my distance for the output or the actual wheel itself. Now, before we move on, let's talk about what distance is. I know in our levers example we said distance. It really, in this example, we'll think of it as diameter. The diameter of the axle, the diameter of the wheel. You could also use circumference. You could also use radius as long as you are consistent. In our example, we're going to use diameter. 0.5 divided by 30 equals 60. AMA, Fout over Fin. Maybe you're given, maybe the wheel is exerting a certain force and the engine for the go-kart is exerting a certain force. My Fout would be the force the wheel is exerting. My Fin would be the force that the engine is pushing the shaft. Fout over Fin. Okay, but what could happen is we could get in a situation where the wheel is actually turning the axle. A knob is a great example. So you just need to realize what the problem is asking and what the situation is. Is it an axle driving a wheel or a wheel driving an axle? All right, let's talk about pulleys. Pulleys are used to lift things. They're very useful. They create a lot of mechanical advantage. They're found in cranes. They're found on the front of engines. Okay, IMA, we count the number of supporting strands if we are talking about one single strand. Here's what I mean by one single strand. In this example, number 2, I go to the hardware store and I'm going to buy one single strand of rope, agreed? So when we have one single strand, we simply count supporting strands. Here's what I mean by supporting strands. We do not count the strand that's in your hand that you're going to use to lift. Don't count this one, we don't count this one. That means that this has an ideal mechanical advantage of 1, this one has 2, this one has 3 strands. It got cut off a little bit. There you go. 1, 2, 3. Sometimes that's not the case. If you have a situation where you have multiple strands and fixed and movable pulleys like this, notice we don't have one single strand anymore. Notice that this is a strand and this is a strand and so on and so on. When I say that what I just told you went out the window, that means we have 2 different methods for calculating ideal mechanical advantage with pulleys. Now, this is a very different setup with separate strands. Once I see separate strands, we do something different. Fixed pulley has a mechanical advantage of 1. Think of that fixed pulley. I drew a lever right here. Commonly we have one person on this side of the seesaw, one person on this side. That would be a mechanical advantage of 1. You can kind of think of it that way. Movable pulley, a rope goes through something like this and it lifts up and it's pivoting out on this end. So it has a mechanical advantage similar to that of a second-class lever. It has a mechanical advantage of 2. What we do is we multiply the mechanical advantages of each of the pulleys together. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, plus this fixed one is 17. Let's do a little practice. Single strand, don't count this one, mechanical advantage of 1, 2, 3, 4. This one, similar to the last slide, so mechanical advantage of 2 for all of these except for this one, which is 1. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, plus 1 is 33. Also, before we leave pulleys, let's go back. Let's go back to this slide. We never talked about AMA, and AMA is really straightforward. The equation is still the same. AMA is Fout over Fin. My Fout is going to be my load. Maybe I have a load right here, and it's 15 newtons, and maybe I'm pulling with 5 newtons. And when I pull with that 5 newtons, that would be my fin, my force in. So I didn't mention that, but that equation stays the same, and that's pretty straightforward. Fout is always your load, fin is always your force in. Okay, let's say this is an activity you guys are going to do in class. All right, let's talk inclined plane. Inclined plane. AMA, we'll start off with that one. AMA, Fout over Fin. Maybe I have a force of 15.23 pounds, and I'm pushing in with 2.3 pounds. 15.23 over 2.31, 6.59, Fout over Fin. Let's talk din over doubt. Let's talk IMA for an inclined plane. The din, the distance in, think about it, the distance you're going to input. Distance you're going to input is going to be along the hypotenuse of the triangle or along the angled part of that ramp. Your doubt, what's the output of an inclined plane? What's its job? Its job is to output this distance. So this distance where I'm drawing right here, the far side, the height of the ramp is your doubt. So din, the length of the ramp, doubt, the height of the ramp. IMA, din over doubt. Last one. Let's talk about screw. Couple things we need to know. You're going to commonly see, just like this red circle, some nomenclature we need to go over. You're going to commonly see quarter 20 NC, or some measurement, and usually 20 and usually NC. The quarter stands for the diameter of the bolts. The 20 stands for the TPI, we call it, or the threads per inch. And NC stands for the thread type, or national course. Quarter 20 NC. Our equation is very different. Our equation for IMA is circumference, C stands for circumference, divided by 1 over TPI. IMA equals, don't forget that circumference is pi d. So pi, and my diameter was quarter, so pi 1/4 or pi 0.25 divided by 1 over 20. 20 was my threads per inch. Gives me a mechanical advantage of 15.7. AMA would be the exact same equation, Fout over Fin. Maybe I'm pushing in or pushing with a wrench with X amount of force, that would be my fin. And maybe the force or the screw is being driven down with some force, that would be my Fout. Before we leave the slide, let's mention, what if I put a wrench? If I put a wrench on this slide, or excuse me, I put a wrench on the screw or bolt right here, what I really did was I elongated I just changed the diameter. So what's going to change is just this part is going to change in your equation, just the diameter. So, but what we need to realize is if I put a wrench, let me redraw that. If I put a wrench, maybe it's this long, this is only the radius. This part's only the radius of the circle, because I'm going to spin my wrench all the way around. Let's say the wrench is 15 inches long, but my diameter is actually 30. Does that make sense? Because I'm spinning that wrench around. A 15-inch long wrench has a diameter of 30. So I'll take that measurement and plug it in here. That's the only part of the equation that's going to change. Instead of pi 1/4, mine would be pi 30 with a 15-inch long wrench. That will increase my mechanical advantage drastically. Okay, last one, wedge. All we really need to go over are our measurements. Let's do IMA first. IMA, din over dout. The distance I'm going to input my wedge. Wedge could be scissors, a knife, an axe, or a hatchet. So din is the distance I put in, the length of the wedge. And the dout is the distance out. What is the point of a wedge? Let's use a hatchet. The point of it is to split something. What distance? This distance. That's my measurement for dout. Let's talk fin. AMA, Fout over Fin. The fin, the force in. What force am I going to drive down this hatchet? And then force out, how much force is going to be pushing out on either side. Promise.
Hey.